Today's best AI reasoning models think out loud. They write a chain of thought in plain English, and that running commentary is one of our best safety tools. We can read it, monitor it, and catch the model misbehaving. But a new kind of model, a text diffusion model, does much of its thinking in a hidden latent space. So DeepMind asked a pointed question. When an AI stops thinking in English, can we still read its mind? First, why the chain of thought matters so much. When a model schemes, hacks its reward, or falls for a prompt injection, the evidence often shows up only in its written reasoning. We can hand that reasoning to another model and ask it to flag misuse and misalignment. Chain of thought transparency is becoming load-bearing for deciding whether powerful AI is even safe to deploy. Now meet the new kind of model. A normal model writes one token at a time, left to right. A text diffusion model instead starts with a whole canvas of random tokens and repeatedly denoises the entire canvas at once, refining all positions together until an answer emerges. It's a fundamentally different way to generate text. And here's the catch. Between denoising steps, DiffusionGemma doesn't just pass plain tokens, it also passes dense self-conditioning vectors that aren't human-readable. So the model might not think in English. It can secretly weigh several options for a token at once, or change its mind on an earlier token, all without any of it showing up in the visible text. To answer the question rigorously, they split transparency into two cleaner ideas. Variable transparency. Do we understand the intermediate snapshots of the model's state? And algorithmic transparency. Can we use those snapshots to reconstruct the actual process the model used to reach its answer? Two different questions, and the paper tackles each. Here's the architecture, simplified. The prompt is prefilled on the left. The canvas, on the right, is a fixed block of token slots, each carrying both a token guess and a self-conditioning vector. Every denoising step runs the whole canvas through the transformer with bidirectional attention, then feeds its output into the next step. 48 steps, all sharing one big bottleneck. To measure the danger, they borrow a metric called opaque serial depth, the longest stretch of serial computation that happens without passing through anything a human can interpret. The intuition is simple. The more thinking a model can do in the dark, between readable checkpoints, the more room it has to hide reasoning from us. The first number is alarming. If you treat those dense intermediate vectors as a black box, DiffusionGemma's opaque serial depth is 28.6 times higher than the matching autoregressive Gemma 4 model. Taken at face value, that says it's doing vastly more hidden, uninterpretable computation. Case closed, diffusion is opaque. Or is it? Here's the twist that flips the whole story. That 28x number assumes the intermediate states are unreadable. But what if we could make them readable? The key question becomes, can we convert those dense self-conditioning vectors into plain, interpretable tokens without breaking the model? Their tool is the Logit Lens. At each step, the self-conditioning vector is basically a blend of token embeddings, so they squeeze it down to just its top few most probable tokens and throw the rest away. It's a hard restriction on how much information can flow between steps. The question is whether the model can still perform once you choke that channel. And it barely flinches. Keeping just the top 8 tokens, or everything above 3% probability, the model matches its full performance across coding, math, and science benchmarks. So the load-bearing information squeezed between denoising steps really is just a handful of readable tokens, not some inscrutable dense soup. Once you accept those intermediate tokens as interpretable, the opaque serial depth collapses. It drops from 28.6 times Gemma down to just 1.1 times, essentially the same as a normal autoregressive model. The scary gap was mostly an illusion of treating readable states as if they were a black box. But are those top tokens actually meaningful? They check on 800 real chat prompts. Turns out the intermediate tokens are overwhelmingly just guesses for the final token at that position, or a nearby one. Above the 3% threshold, more than 85% of them are interpretable, even at the very first denoising step. The canvas isn't hiding secret reasoning, it's mostly drafting. So can a real monitor actually catch this model misbehaving? They run DeepMind's Monitorability suite, where a separate model reads the reasoning and tries to detect things like a planted intervention or a flawed solution path. The result, in blue versus orange, DiffusionGemma is about as monitorable as autoregressive Gemma 4. And that's despite a real handicap. DiffusionGemma writes much shorter chains of thought than Gemma, and longer reasoning is usually easier to monitor, so if anything, that confounder works against it. Yet it still keeps pace. In the headline safety metric, the diffusion model holds its own. Now for the genuinely strange part, algorithmic transparency. Because diffusion can rewrite any token at any step, it can reason in ways an autoregressive model simply cannot. The team ran a series of case studies and uncovered brand new, diffusion-specific phenomena. This is where it gets fun. Start with something almost eerie. The model predicts how long its answer will be before it knows what it will say. Ask it to explain photosynthesis in 2 sentences, and after a single denoising step, it is already locked in padding everywhere past about position 55. Its very first length, guess nails the final answer length. It plans the shape before the content. Now watch it literally change its mind. They ask how many square numbers lie between 400 and 800. Answer first, then reasoning. At step 4, the model confidently writes 9. Then it works through the reasoning, computing the square roots, and goes back and corrects its own earlier answer to 8. An autoregressive model could never do this. Once it writes 9, 9 is frozen. This is retroactive self-correction, and it's a superpower autoregressive models lack. The model can leave an answer tentative, do the work elsewhere on the canvas, and then reach back to fix the answer it already wrote. They also see the dark side. Sometimes it locks in too early on a wrong answer and can't shake it loose. Then there's smearing. Sometimes the model knows a word it wants, but not yet where it goes, so it spreads that token's probability across several positions at once, token smearing. More dramatically, in sequence smearing, it holds 2 whole candidate sentences in superposition, a kind of built-in beam search, before collapsing onto one. The reasoning genuinely isn't a single clean draft. The most important one for safety, intermediate context reasoning. They give a Fibonacci-style task where every digit 3 must become the word gold. The model first writes the digit 3, uses it to compute the next numbers, and only then overwrites it with gold. That 3 was essential scratch work, causally necessary, yet it never appears in the final output. So what's the verdict? Reassuringly, today's DiffusionGemma is roughly as transparent and monitorable as its autoregressive cousin, once you read the intermediate tokens. The hidden computation is mostly drafting, not scheming. But intermediate context reasoning is a warning shot. In principle, this architecture can do load-bearing reasoning that never reaches the final text. The authors are careful. This transparency may be a lucky artifact of how DiffusionGemma was trained, that projection biasing the vectors toward real token embeddings. Train future models differently, with heavy outcome-based reinforcement learning or bigger canvases, and the latent space could go dark. Their real goal is a template. Audit every new latent reasoning model this way and watch for regressions. So here's the one-line takeaway. A diffusion AI thinks in a strange, non-linear way, planning length first, changing its mind, holding 2 answers at once. But for now, if you read the right intermediate tokens, you can still follow its reasoning about as well as a normal model. The mind is readable for today. Thanks for watching.